This is section 1.2. We're going to look at linear modeling, and this is part B of the section. We're going to be using algebra to make what's called a model or an equation that represents some real-world situation, which is often going to be given to us in the form of a data table. In our first example, we have a table that shows us the number of credit hours, H, is our independent variable in the left column, and the cost in dollars, C, is the dependent variable in the right column. We're going to first of all use a scatter plot to decide whether the data are linear. In order to do that, we'll use our TI-84 and we'll input this data. If you haven't done this before, I'm going to walk you through the process right here. First of all, what you want to do is put the data in, and to do that we use the stat area, stat for statistics. Option number 1 is edit. And that's exactly what we want to do. We want to edit the data in the calculator, so I'm just going to push enter. I don't have any data in here right now, but if you do, you can get rid of it by using your arrow key to go up, highlight the name of the column, L1, and push clear. Enter, and when you come back down, all the data should be gone. All right, let's put our data in for the first column, the credit hours. 3, enter, 7, enter, and so on. All right, I'll use my arrow key now to move over to the second column. Again, clear it if it's not already cleared. And this will be my output variable, my costs in dollars. So we'll put in all of those values. And my data is now all in the calculator. And I'd like to look at what this data looks like. So in y equals, go in and make sure your plot is highlighted. It may not be right now, and all you have to do is use your arrow key to go up where it says plot 1 and hit enter. I just turned mine off. It's like a toggle switch. So I'm going to go back up and hit enter again, and that should turn it on. The next thing we want to do is set our window so that the calculator knows how much of this or how much space it needs to look at. So in the window, I can see that my X values, or my inputs, my credit hours, run from 3 to 18. In order to give it a little space, I'm going to say 0 to 20 for the X min and X max. 3 to 18 certainly fits nicely in there, and a scale of 1 will work fine. The Y's are actually C's, the costs for me, and they go from 315 to 1590. I'm going to go 0 to 2000 for my Y min and Y max. Again, that will certainly cover the values in my table. And I'll use a scale of 100. We'll count by hundreds. We should just be able to hit graph now. And notice that your points are plotted right over here. And they do indeed look like they line up pretty well. They're very, very close and probably even exactly on a straight line. All right, so we verified that the data certainly do seem to look linear. Now that I've done that, I'd like to find an actual linear function that fits this data. And in order to do that, I'm going to do it by hand, although later we'll use the calculator for it. I'm going to use the first 2 points in my data table to do the calculation. You know that by hand we can only take into account 2 points. The calculator will be able to take into account more than that when we start talking about that. I'll begin by finding the slope, which would be difference in the y's, 655 minus 315, divided by the difference in the x's, 7 minus 3. And if you just put all that into your calculator, you should find that the slope turns out to be 85. To get the y-intercept, I'll use y equals mx plus b. And it doesn't make any difference which point I put in. I'll go ahead and use the first one. Y is 315. We just found out that m was 85, and the x over here is 3. Plus b. Again, just going ahead and doing the calculation, I get 315 equals 255 plus b, so b turns out to be 60. All right, my equation then is y equals m, which is 85, x, plus b, which is 60. But the problem specified that I need to use the variables given. So instead of y, I'm going to use c. The y column is actually the costs, or c values. And instead of x, I'm going to use h, the independent variable. And then one last thing, if I need to use function notation, I can say, well, c depends on h, so I could write this as c of h equals 85h plus 60. All right, we're going to go ahead next and just take one more look at the calculator, because I'd like to see how close I came to my points, or if I did a good job. Going back to our calculator, we can put the equation y equals 85x plus 60 in and see if it matches up with the points. In order to do this, I'll go to y equals. And again, notice that we have to use x and y for the calculator, even if we use different variables for ourselves. So I'll just type in my equation, 85x plus 60. And then I'm just going to hit the graph key again. And I can see we did a great job. Our line certainly does seem to go nicely through the points that we had. One of the things we'll be asking you to do a lot is to interpret the results that you have. So here it says the slope m of the function that we found represents what? Well, our slope was 85. And that 85 actually represents the change in cost per credit hour. When I'm looking at interpreting slope, I'm always going to describe the slope as a change in the dependent variable, in this case cost, per change of 1 in the independent variable, in this case credit hours. So again, I can describe this by saying the cost increases, since it was a positive slope, by $85 per credit hour. In other words, the school must charge $85 per credit hour for their class. The second interpretation we'd like to make is the interpretation of the y-intercept, the b value. And in this case, our b value turned out to be 60. The b value, or y-intercept, is what we get when x is 0, or in this case, when h is 0. So that would say that if you take 0 credit hours, the cost is $60. That might seem a little fishy. Let's write it down first, and then we'll talk about whether it makes sense. The cost of 0 credits is $60. What that probably is a registration fee or an activity fee of some kind. You all know that although you don't really have to pay it if you don't take any credits, as soon as you take credits at all, they're going to charge you that $60 on top of your credit hour or on top of your tuition fee as something like a registration fee. right, so let's look at the next example. In this problem, it says accountants for large corporations keep track of the value of company equipment for tax purposes. A common method for doing this is called straight-line depreciation. In our table, we see some values of T, that is how many years it's been since the equipment was purchased, and then our dependent variable is V, the value of the equipment after that length of time. First, we're asked, how can we tell that this data is linear, even without doing a scatter plot on the calculator? Well, there's sort of a regular pattern to this data that tells me that it's linear. Notice that the input, the T values, always go up 2 at a time. Consistently, they change by +2. And at the same time, the dependent variables, the V's, decrease by 10,000 every time. When consistent changes in the input variable result in the same constant change in the Y variable or output variable every time, that tells me that the data is linear even without doing a scatter plot. Let's go ahead and get the equation for this data. I've really kind of almost done the slope calculation just by what I wrote down there, but I'm going to write it out anyway. I'll go ahead and use the first 2 data points. So that would be subtracting the y's, 50,000 minus 60,000, and subtracting the x's, 2 minus 0, gives me a slope of -5,000. Now this problem is particularly nice because I don't have to work very hard to get the y-intercept. Notice, I actually already know it. I know that when the input, or x, is 0, the output, or y, is 60,000. So that point right there tells me b is 60,000 without doing any more work. When you're given the point where x is 0, it's a particularly easy problem to work because you already know the y-intercept. Okay, well that tells me that my equation is actually y equals m, or -5,000x, plus b, or 60,000. And if I want to write this in function notation using the variables in the problem, the y is actually the v. So I'm going to write v of t, since it's going to depend on the time, equals -5,000. And again, the x is actually the t value here. So -5,000 t plus 60,000. Our slope in this case, the -5,000, again tells me how the dependent variable, v, is changing with respect to the independent variable, t. In this case, v, the value, is decreasing, since it's negative, by $5,000 per year. Years are my input variable. So the value is decreasing by $5,000 per year. Slope always tells us about rate of change. Something's either increasing or decreasing, and you need to tell me by how much and per what, per year, per hour, per whatever. The b value we've talked about a little bit. B was 60,000, and that's our starting value. At time 0, when the equipment was originally bought, it was worth $60,000. There are times when data doesn't lie exactly on a straight line. And when that happens, we can still use a linear equation as a model if the pattern is basically linear. So the first thing we're going to do is we're going to find we're going to look at our 2 sets of data here and figure out which one, if either, has data that is pretty much linear. Once we figure that out, we'll find what's called a line of best fit. The line of best fit is actually something the calculator does for us using a process called regression. Although these points won't lie exactly on a line, the calculator will find the line that comes closest to all of the points using this process. So let's take a look. We have two sets of data. The first one, for various years, gives the number of men's colleges, all men colleges in the country. And notice that there are some definitions here that we should be careful of. T is said to be the number of years after 1960. So when I put this data in my calculator, I'm not going to put the whole 1967. Instead, I'm going to say, well, that's actually just 7 years after 1960. So when I put it in my calculator, I'll just put in the 7. Continuing on down the list, 1975 is 15 years after 1960. 1985 would be 25 years. 1995 would be 35 years. And 2012 would be, what, 52 years? Of course, I'm just subtracting my year minus 1960 each time. Okay. So we'll go ahead and put that data in the calculator. And once again, I'm going to do this one with you. Let's grab our calculator and go into Stat and option number 1, Edit. And the first thing I'm going to do is clear the old data out so that I can put my new data in and not worry about any carryover. And again, I'm going to put the t values, not the actual years, in. And then in the second column, I'll put my output variables and the number of all male colleges. When you go to y equals, you'll want to clear out your old equation, since we're not looking at that particular example anymore, and just make sure that plot is still turned on. In the window, I can see that my t values went from 7 to 52. So I'm going to go 0 to 60 with a scale of maybe 10. My y values are between 4 and 145. I'll go 0 to 150. And maybe use a scale of 10 on that. If I now hit Graph, I can take a look at the scatter plot down here. And I can see that there's really no good straight line that would come very close to all of those points. If I tried to draw one, I'd miss one by a lot. Right? Or if I tried again, maybe I'll do it this way. But now I've missed this one by a lot. So there's no single straight line that comes pretty close to all of those at the same time. This data is not very linear, and it's not going to be a good choice for us to do a linear model on this. Let's take a look at our second set of data. This data shows us for various years the value of yogurt sales in the United States. If I look at my definition of t in this one, t is the number of years after the year 2000. So if I add that information to my table, 2001 is just 1 year after 2000. And then I would have 3, 5, 8, and 10 years after the year 2000. We'll go ahead and put that data into the calculator. I'm going to do it kind of off camera here, and if you'd like to pause the video and do it yourself so that you can have the same data in, that's fine, but I'm going to show you the done situation in just a moment. So here I have the data already in the calculator, and I'm going to go ahead and set up my scatter plot. Under my y equals, I really don't need to do anything because the plot's already turned on. When I go to my window, the first column goes from 1 to 10, so maybe 0 to 15 there. And the second column, maybe 0 to 5 would certainly cover all of those points. So when I go to my window, I'm going to try 0 to 15 with a scale of 1 for the x's, and just 0 to 5 with a scale of 1 for the y's. And I'm going to graph that. And I can see that this time, although it's not a perfect line, it's not bad. I could imagine drawing a line on here that would come pretty close to all of those data points. I'm going to miss them by just a little bit, but unlike last time, I'm very close. So this time, a linear model is a really good choice. Now we already know that we could come up with a linear model by hand by selecting 2 points and finding the equation of the line. The calculator, though, can do a better job. It can take into account all 5 data points. So I'm going to take a look at how the calculator does that. On my calculator, back in the Stat menu, I'd like to calculate. So I'm going to use the arrow keys to move over and select Calc. And I'm looking at option number 4, the linear regression. I'll say Enter, and all of this is correct. We've used lists 1 and 2. Just keep hitting Enter until you get down to Calculate. And I'm going to enter one more time. And notice that what it does for me is it gives me an A and a B. That's really an M and a B. The calculator just uses the letter A, but it's the same thing. So the calculator is telling me the equation of this line is 0.19x plus 2.09. Let's write that down. I can rewrite this using the variables in the problem by simply using a capital Y for the output variable, yogurt sales, and a T for the input variable, time. The problem also asks us about the slope of the line of best fit and what it represents. Our slope is 0.19. And in this case, it's telling us about how the yogurt sales are changing with respect to time. So I could say the yogurt sales are increasing since I have a positive slope. By 0.19. And be careful of the units here. The yogurt sales were given in billions of dollars. So that would be by $0.19 billion per year, since T was given in years. Notice, although I didn't ask, we could also interpret the B value. B here is 2.09. And B is always the starting value, or what was happening in the original year. Our original year, when T is 0, would be the year 2000. So what this tells me is that in the year 2000, yogurt sales were $2.09 billion. Okay, this problem actually also asked us to compare what we get by the calculator to what we might have gotten by using just 2 points and doing it by hand. So let me real quick do a by hand calculation just for comparison. If I'm doing this by hand, I need to select 2 points. And I'm going to go ahead and choose the first point and the last point to work by hand. The first point really had a T of 1. And the sales were 2.3 billion. The last point time was 10 years, and sales were 4.1 billion. I'll just do a traditional calculation here. y2 minus y1 divided by x2 minus x1 gives me the slope. And if you grab your calculator and do that, you find out the slope is actually 0.2. Notice that that's very close to the slope of 0.19 that the calculator found for me. To get the y-intercept, I can go with y equals mx plus b. And I'm going to plug in the first point. Y is 2.3, m is 0.2, and x is 1. So 2.3 equals 0.2 plus b, and subtracting the 0.2 gives me 2.1 for b. Again, very, very close to the 2.09 that I got when I did the regression on the calculator. So in this case, working by hand, yogurt sales would have been capital Y equals 0.2t plus 2.1. As we'll see, in a case like this, we had a really good model. The original values must have been very close to truly linear, because what I got by hand matched up really well with what I got by the calculator. Sometimes we won't do quite as well with that, depending on how perfectly linear or nonlinear our data is. I'm going to end this segment of the video right now, and we'll look at part C to finish the segment.